if you have a good grasp over these basic concepts of linear algebra, then you can start looking into the field of quantum computing. First year is the best time to get into this because you get about if you get about 3 to 4 years at least in while you are in college, while you can build your base. If you are a startup or if you are a let's say a new entrepreneur and you go to a VC and you pitch something related to quantum, they'll throw money at you.
So, hey everyone, welcome to the first episode of QCafé. We have Abhigyan Mishra from BosonQ and QFitix here to discuss over the introduction to quantum computing for first year undergraduate and anyone who wants to start in this field. So, hello, Abhigyan Mishra. So, would you like to have our audience a quick intro to you and what you do?
So, hey Ashmit, first of all, thank you for the opportunity and giving me a platform so that I could, directly talk to you in the first year student. Because see, the thing is that the first year student present to be the greater demographic, right? These were the people that will, in future, would come into the whole quantum industry or the community itself. Okay, so starting with my bit introduction about myself. So my name is Abhigyan Mishra. So currently I'm the senior quantum computing developer and the quantum lead at BosonQ Psi, which is an Indian-based quantum computing startup. And I'm also the founder of IFTX and also biscuit advocate at IBM Quantum. So, that would be a short a bit of introduction about myself. And also, I come from a computer science background for those who are interested. So currently, I just completed my master's in computer science, and so for those who come from not from physics background, who don't come from, I would say, your STEM background, though you can still understand. I mean, I would be the best example to demonstrate that it's not important that you have a degree or you have a I would say expertise in quantum mechanics itself, or the physics side of things. You can always get into this field, even though you are coming from a computer science point of view. So yeah, I mean that would be a bit of introduction about myself, and yeah, looking forward to the conversation.
So, when talking about quantum computing, there we have a classical computers all around. So, when talking about quantum computing, what is the basic difference that someone from not from this background can understand? And what, like in basic
Well,
term,
that's a
what is
very
quantum computing?
Yeah, I mean, that's a very good question. And I mean, I can understand, why this question. I mean, see, basically now that I have taken like multiple sessions, I have, I would say met people from, all kind of backgrounds, from electronics to, physics, from computer science to say, even some people from arts background. So I can confidently tell you that, this question, which you particularly are, that it's a valid question. Well, so see, to answer your question, I would like to, take a step back actually. So, when we mean all of us are familiar with the history of classical computers at least, right? Like, those who, like in the basic unit of any computer is a bit, right? And a bit in a physical implementation is like a transistor, right? Which goes on and off. Pretty simple, pretty basic stuff. Everyone, I think we study about this in, seventh, eighth in computer science and in, a subject. So I mean, I won't elaborate on that, but so, there's this law, which is this law called Moore's law, which says that, after every 2 years, the number of transistors on an integrated circuit just doubles. I mean, that is in some sense of way saying that, we are doubling the computation power of a classical computer almost every 2 years. But see, there is a limitation to that. When you are saying doubling the number of transistors, you can see there are two ways of doing that, right? One is to make this IC a bit larger, and the other is to make the transistors smaller. Yeah, so I was saying that, see, so the thing with this the whole Moore's concept is that when you are trying to double the number of transistors, the best possible way is to just make the transistors smaller, right? But see, the problem with that whole aspect is that once you reach a particular level of size, you know then you are basically entering the quantum mechanics realm, where your classical logics and these kind of normal logic which we are used to, those don't make sense anymore, right? They're like you can say phenomena like quantum tunneling, right? And those things affect the transistors negatively. So definitely this is not the way to go. Like, see, I mean, I won't say that the quantum computing is the only way possible, right? There are like molecular computing, and there are other fields of aspects to it, like which Intel and AMD are working on. But see, quantum computing is expected to be one of those solutions. Now, what exactly is a quantum computer? Well, see, I talked about this concept of bit, right? We have the 0 and 1. So see, a bit at any point of time could either be one
or zero. I want you to, understand and, keep this or term in your mind. So at
Hmm.
one point of time, we can either have a zero or a one, right? But in the quantum computers, there are concepts like, you can say superposition, which allows you to, basically work with a state which is in between of these two. I mean, see, between is not the correct way to term to use here, but see, just for the sake of simplicity, I'm using it now, right now. We so there's a whole, you can say, an exact definition of superposition that I'm not getting into right now, because see, I'm
Hmm.
trying to keep it as simple and as abstract as possible for now. But for now, you can understand that, say, I'll give you a very good example. So I think this should basically clarify this whole aspect. So when you
Hmm.
have n bits, so if you have n bits, then it's, in classical sense, that you can represent any state from 0 to 2 to the power n, right, at one point of time, but only one at a time, right? See, in quantum computer, I'm basically telling you is that I can represent all the 2 to the power n possible states simultaneously. So
Hmm.
see, you can make out what the, you can see, the benefit here is, right? It's one state versus 2 to the power n states simultaneously, right?
Hmm.
So that gives us a computational boost, basically, and to now, okay, all this being said, there was a context to now come into your answer. So see,
Hmm.
what is quantum computing? So you see, the quantum computer comprises of two words: quantum and computing, right? As simple as that. See, the
Hmm.
quantum aspect is, the quantum mechanics aspect, the all the postulates of quantum mechanics, and the mathematics, and so on and so. And the computing part is what, I as a computer scientist work on. Computing is
Hmm.
just solving a problem. So what we are basically doing is, we are applying principles of quantum mechanics to compute certain problems in theoretically efficient ways. Right now, I mean, I wouldn't say that it's always beneficial, and you can, if time allows, I'll, probably tell you that, what kinds of problems, which we can, probably tackle on a quantum computer. But for now, I'll say there are only certain kind of problems that a quantum computer could, you can say, solve efficiently. But when it does, we get a significant performance boost. And the reason, one of the primary reason being the one at which I told you, prior to this, the superposition thing, being able to represent all the 2 to the power n states simultaneously. That's,
Hmm.
more or less it. So yeah, I mean, for now, I'll keep the definition to this. you know as we move ahead in the discussion, maybe, I'll add a few things here and there, and yeah.
So, when I was starting with the quantum computing,
Hmm.
I was like wondering, is this field for me or not? So,
Hmm.
I was in BTech first year, so it was for me all around there were students of PhD and master's degree who were pursuing this. So, is
Hmm.
it for undergraduate students also, like for whom this field is for?
See, that's a very good question. So, I mean, see, I mean, in very essence, I mean, I'll just quote, one of the, the textbooks from IBM itself, from the Qiskit textbook. So the basic prerequisite for the whole quantum computing, getting into quantum computing, at least, I won't say expertise or, doing some legible work in it, but just getting to understand and, trying your hand on quantum computing, you just need a basic understanding of linear algebra. Right.
Hmm.
I wouldn't even say, you need to understand quantum mechanics for now. If you just need to enter quantum mechanics, this whole, quantum computing, right?
Hmm.
So, see, so in that aspect, I would say, anyone, who has the, I would say, I mean, because, I'll say that I'm right now addressing Indian audiences. So I'm already familiar with the, the curriculum from NCRT from 11th and
Yeah.
12th, because yeah, I also come from a physics, PCM background. So the
Hmm.
thing is that, your basic, if you have a good grasp over the, your 11th and 12th mathematics, your concepts like matrices, determinants, linear algebra, right?
Hmm.
So I mean, those who, come, who are, I mean, basically present, I'm, talking to a demographic of first year students. So
Yeah.
you do understand that linear algebra is not limited to, your just basic algebras. It contains your vectors, it contains your, what you call your determinants, your matrices, right? All those aspects. So if you have a good grasp over these basic concepts of linear algebra, then you can, you can start looking into the field of quantum computing.
So I was saying that, see, what you said that, what kind of prerequisite do you need? Basically, that is how this question sums up to. See, the basic, I would say, the prerequisite is just linear algebra. But more than that, it's about, having the correct mindset, when you are entering this field of quantum computing. Like, I mean, I'm probably assuming that you'll be asking this question anyway, that, people do think that quantum computing is hard. What do I have to say about that? So I agree. And quantum computing is hard. It's supposed to be hard, not because of the hefty mathematics and the quantum mechanics, the physics. It's supposed to be hard because see the concepts which you have to you can say understand, and you have to accept while you're working on a quantum computer. You are not used to those concepts. Like there will be like terms like quantum superposition, entanglement, coherence, decoherence, right? And phase kickback, and these terms. When you read about it at first glance, they won't make sense. Like, see, I'll take a very simple example of this entanglement. I'll try to keep it simple. So, entanglement is basically, when two particles, are said to be entangled, basically. When, even though they are separated by huge distances, they can still interact with each other. So
Yeah.
think about it. Now, this simple sentence, if I might have said it, in a very quickly, right? But if you think about it, it won't make sense to you. It's like
Yeah.
I'm saying that I am keeping two particles that are separated from each other and in completely different space, and and I would say I'll just use another term, a physics term, that they are, isolated from this environment, so it has that
Yeah.
nothing can affect it.
Yeah.
Right. So, I mean, this kind of system, if those who come from physics background should be deterministic, right? Because you are already deciding the environmental conditions, you should know how the particle will interact because you know everything, and also know the second particle. But yet, if if you knew the properties of one of the particles somehow, in some magical way, I would say for now at least, you can predict the properties of the other particle if they are
Yeah.
entangled. So this does not make sense, right? So it's a basic journey of quantum computing. If anyone asks me, how does the the roadmap, or even not the roadmap, I would say how the difficulty curve for quantum computing goes, I'll just use a simple term. Start with simple linear algebra, right? Start reading about. Okay, I mean, I would say like get into the mathematics directly. Just try to grasp the intuition. Try to get what we are doing and why we are doing. Right.
Yeah.
And see, when you start doing that, you'll keep on growing in this whole aspect, and then you'll reach a point, when you'll feel that now you understand quantum computing. Right. And that is the point, that is when you start looking into mathematics and everything falls apart again. I'll be very honest, everything falls apart. Because now
Sure.
you start looking at the maths and stuff. But the thing is that after that is a different thing. Then you're trying to gain expertise. You're trying to become an expert in this field, right? But just entering, trying to see if this is something you want to invest your time into, is just you require basic understanding of linear algebra, right? And the thirst of knowledge, and just being able to read through stuff, and the funny enough, bear with it. If you start with a chapter on quantum computing, the very first chapter. So I'll take an example of this. Mike and Ike, I mean, it's called the Bible of Quantum Computing. For anyone who's looking into, it's definitely a good read. So the first
Yeah.
chapter won't make sense to you when you read it the first time, if
Yeah.
you don't come up with if you don't come from a physics background, right? But then you can refer to other books. If you say, I was a computer scientist, I read through this book of quantum computing for computer scientists. It's a very good book. I mean, for me at least, it worked. So then you go through that, and then you again come back to this book. So it requires a bit of hard work from, you can say, having the patience, right, to not get it, not get something at the first glance, but being able to read it again, to understand it the second time and then the third time. That I can assure you, mathematics won't is not a huge bottleneck as people keep try to tell you. It's the you can say the patience to understand something, even though it won't make sense to you the first time. If you have that, then quantum computing is a field for you. Just try your hand in it. If you love it, it's and honestly speaking, it's a very cool field. You
Yeah.
once you go around talking to people and you tell them that you're working in a field called quantum computing, so it will seem to them to be a sci-fi thing, right? So it's a very cool field.
Respect.
Specifically, when you're entering your first year, yeah,
Yeah. So like
you can go
when
to
I
hackathons and say and stuff. Yeah, yeah,
yeah.
yeah. Please go ahead. Yeah.
So like in my last in the journey of last 1 year, so it was a time
Hmm.
like when I literally quit from quantum computing. It was like I
Hmm.
can't understand it. So it was like a lack of guidance, like how to actually go through the topics and how to prepare for myself. So what should be the roadmap for first year or second year students?
Yeah, I mean that. Okay, now see the roadmap. See, this question itself, I'll give you an abstract answer, not because I don't want to give you an direct answer, but because I want to keep this as open as possible. Yeah, so I was saying that, see, I mean, I'll try to keep my answer in an abstract way so that, the first year student who are coming from, like, you come from a physics background, yeah, you come from a engineering physics, right? So you'll
Yeah.
have, I mean, specifically, you'll have a different roadway, and those who come from a CSE background, computer science engineering, will have a different road. But see, I'll talk about the basics first. So, start with I would say because see, being very, very honest, all of us have studied mathematics, linear algebra in 11th and 12th, but we never paid too much attention to it because it was not that, that,
Yeah.
people are mostly, studying in that for entrance-based exams, right? And those
Yeah.
don't carry any weightage because those are simple. Those are very
Yeah.
simple. The
We
questions which,
we
come from
need
those
just
topics
to
is very
pass.
simple.
Yeah.
Yeah, and that too, and see, concepts like determinant and matrices are, we call them scoring because you don't get hard questions on that in your exams, right? And that is
Yeah.
true, that is true. But see, actual linear algebra is a bit different than that. I mean, you already know. I mean, you said that you have, you've tried your hand in quantum computing. You know that actual implementation, the use cases of the concepts like determinants, right? This matrices, this tensor product, these things actually, you get to do in quantum computing, right? So first of all, I would say, just to just brush up all your concepts, right? There are great books out there on linear algebra. I'm not saying that you should understand everything right now, at least. Not like, you should be able to solve everything. You should be like a master in linear algebra. But, excuse me, just brush up your knowledge, before you step into it. And then I would say, before you get into real quantum computing, get a brief of what quantum computing actually is. Like, see, what actually is here is that I'm not talking about, reading books and stuff. I'm talking about reading articles, right? There will be, I mean, if you want, I mean, I can share, I mean, I have a list of resources, which I mean, so that, yeah, I mean, which I made, so I'll share it with,
Yeah.
Ashmit, and he can probably add it in the description, so that could be the possibility. So it contains a list of all the blogs, and, it again contains tutorials and videos, all that kind of stuff. So start with some articles, read one or two articles, and why quantum computing, why do we even care, you know so see that and what I'm why I'm doing this is why I'm saying to do this is to ignite that spark. Because see, as you'll move ahead, I mean, there will be times where when you'll not understand certain stuff, and you will feel demoralized. You'll feel like, okay, I'm investing so much time in it, and still I'm not able to understand what's the use, right?
Yeah.
At that moment you need to realize the impacts and the implication of the work which you'll be doing if you remain in this field. So start with that, do these two things to get a sort of like a this is like a you can say what you call a prologue type of thing, right? This is like a prologue. Now actually coming to the the real roadmap. Start with, I would say the best way to start is this Qiskit textbook. This is
Text.
it's made by IBM. It's Qiskit textbook. Yeah.
Yeah.
So it's pretty good. I mean, it's a step-by-step process. It's a step-by-step process. You start from a very basic knowledge, and the thing with it is that, see, I mean, okay, although quantum computing is not restricted to just quantum programming and quantum development, there is a hardware aspect to it as well,
Yeah.
right? But me, coming from a bit biased because I know I come from, again, a programming background, a computer science background. I would say it's good. It's very good to to build intuition if you keep coding it as you learn it, right? And the
Yeah.
coding language I'm saying is Python. So no, I'm not even asking you to learn C++ or Java and stuff.
Yeah.
Python is pretty basic stuff. So I mean, it's not even a prerequisite. Even if you don't want to do it, don't. It's completely fine. But I would personally, and it's like I would say I would recommend doing it so that you can build intuition. Just
Yeah.
go through that Qiskit textbook, right? And once you're done with that, now I will say, now comes the specific part. Now it comes the part where you need to be specific to the type of field in which you want to work. Okay, now say I come from a computer science background, so I picked a book which was more catered towards the computer scientist, right? Like quantum computing for computer scientists, quantum computing developments, and it was this another book by O'Reilly. I'm forgetting the name, Quantum Computing Handbook or something. So these things, the list I'm sharing with you that it will
Yeah.
contain
Sure.
everything. Okay. Now that is for like software kind of things, and then there's Mike and Ike, for quantum information theory. and more some more certain books in quantum information, that could be someone who comes more from a physics background. Now,
Yeah.
again, this, although I'm dividing only in two parts, but I would like to say that those who come from, again, from anyone that comes from non-physics background, basically, I would say take a developer's path for now. Take the path of, this development routine, which is the computer science path.
Yeah.
Why I'm saying that is because, see, the computers in computer science aspect, we try to build the intuition first, right? And
Yeah.
then we code. So even if you understand the intuition, then it's good enough for you. Right. And okay, while you're doing this is from the literature point of things. And other is, again, this is sources which I'm sharing. It will contain you can say playlist, YouTube playlist, and I mean some Coursera courses. I wouldn't say it as, okay, this I'll come to this part later, but I have some playlists, YouTube playlists.
Yeah.
Watch through them, go through them, right? Do all this, in parallel. And by the end of it, I can 110% assure you, you will know what quantum computing is.
Yeah.
That is to do what quantum computing is now. While you're doing this, if you get opportunities like hackathons, like IBM organizes like 2 to 3 hackathons every year, and now even private institutes organizes hackathon, you know.
Yeah.
So participate in these kind of things, even if you don't know much, and if you are not confident enough to develop something, work with other people, get to know that how they are implementing ideas of quantum computing into real world projects, right? See, and the thing with quantum is that it's a very niche field right now. So
Yeah.
people, there are not too many people, and the people who are in quantum computing are very welcoming, let me tell you. Like, they'll welcome you with open hands, and they'll be like, okay, whatever questions you have, howsoever silly it is, they'll answer,
Yeah.
right? So connect with these kind of people, gain as much knowledge as you can from them, and just do these things. And while you're doing this thing, you'll automatically see that you reach this point at a point where you think you'll know quantum computing. Right. And once that is the case, then you start looking for opportunities like internships, you know, and full time. So I would suggest going directly, but look for internships. Go look for what do you call projects with companies, or projects with researchers, whatever that is, and gain knowledge. Keep on gaining knowledge, and yeah, if you reach this point, then you already know what you're doing. If you have
Yeah.
already reached to that point where you are doing multiple internships with quantum computing, you already know what you are doing.
Yeah.
After that, you can just basically choose whatever you want to do. So I'm just trying to cover how you enter this field, and what you should do if you're when you're entering this field. After that, it's an open field. The best thing about fields like deep learning, quantum computing, this machine learning is that these are very niche field. So they have a a full open aspect of whatever you want to do. They give you this opportunity of, okay, we will tell you what this is. Now what you do with this knowledge is completely up to you.
Yeah.
So you can learn quantum computing, but what you do with this quantum computing, how well you can use it to solve a real world problem, is up to you. But that comes again later. But for, I mean, this, and I would say, first year is the best time to get into this, is because, you get about, if you get about 3 to 4 years, at least in, while you are in college, while you can build your base, so that, after 4 years, say, you are ready for the industry. you know.
Yeah.
And by the pace at which the quantum computing is growing, let me tell you, after 4 years, I mean, yeah, I mean, it might be the next huge thing. See, quantum computing is like machine learning, but 10 years ago. It was growing, it was new. We did not have the hardware back then, but we had
Yeah.
algorithms. And when hardware, now if I tell you machine learning, you already know, like GPU, like, parallel processing, everything. Now,
Yeah.
machine learning is so common. So quantum, we at a certain point of time will reach that point where the hardware will be so good that everyone will be using quantum computing.
Yeah.
Right. So it's like prepare for the future.
Yeah. So
By
when
just
it comes to like many companies says like quantum is in next 5 year quantum will grow so much, and some say it will take more time. So what do you think? What is the future of quantum? Near future and long term future.
See, I would say, see, right now, what we call, we live in this era called NISQ era. This is, I mean, I mean, I'm just, you can look it up if you want, but it's like noise intermediate, a scale quantum, NISQ era. So the devices which we have right now, the quantum hardware which we have right now, is not very scalable. We cannot like run huge algorithms on it right now. Right. But see, the thing here is that although that is the possibility, that is the case, but as I said, those who come from a physics background or an electronics background can definitely get into the field of quantum hardware. Those people who are dedicatedly responsible for improving the quantum hardware which we have, right? So we are making progress at a very fast rate. Like, we already have about, I mean, say 58 qubits publicly available by the companies like IBM and Rigetti. And we are supposed to have like 100 plus qubits from IBM in the span of next 2 to 3 years, right? So see, 100 qubits is a very big thing, let me tell you, like from a very technical perspective. But as we move ahead, the rate that we are progressing in the next decade, we are looking at a full-fledged quantum computer that will solve industry standard problems, right? So right now, what we are doing at this point of time, we are making softwares, we are making applications, we are making simply code that in the future can run well on a quantum computer.
Yeah.
That is one thing. Other thing is that, see, like the company which I work at, like BosonQ Psi, so we will also develop quantum inspired algorithms, like quantum ready, I would say. See, what that means is that even though we don't have right now have the correct hardware to run these algorithms, right, to its full scale, but we still can run it or simulate it on a classical hardware and still get better results. So, I mean, I'm throwing a lot of terms here. So, I mean,
Yeah.
if you have a shortage of time, I'm going to elaborate each one of them. But yeah, for those who are interested, quantum-inspired algorithms are basically algorithms which uses some aspect of quantum mechanics and simulate it on a classical hardware, your basic classical hardware, to get better results. So that is
Hmm.
something which I right now am working on. But that, I mean, and, okay, to be more precise, I work on quantum optimization algorithms. So yeah, that is somewhat my domain. And yeah, I mean, with that, to answer your question, we are right now in a phase where we are developing code that would scale well when we have the correct hardware, but will also give us performance boost right now.
Yeah.
So yeah.
So like most of the students when they come to college, they are like job oriented. Like they always see what how much they will earn in next 4 years and which job they will do. So what are the job opportunities present now and will be present in next 5 to 6 years?
Yeah, I mean, okay, that's a very practical question, and I feel like that is most important to answer out of every question. Yeah, I mean, let me tell you, this is a very, very, you can say growing field, very growing field. Like, I mean, I don't know if I should say this or not, but if you are a startup or if you are a, let's say, a new entrepreneur and you go to a VC and you pitch something related to quantum, they'll throw money at you.
Yeah.
Why is that? So, some people would say that, okay, I just in the previous question I said we don't have the correct hardware, we don't have the best hardware. So why are people investing so much money and time in it? So see, I mean, although I mean, as I said that although the hardware right now is not that adequate, but see, I like to use this analogy whenever I'm explaining why quantum computing is growing so much. So it's like I would say, what do you call, like an insurance thing. you know I mean, you don't want to get hurt, you don't want you don't want to get into an accident and stuff, but you do it because just in case, right? It's similar to that, like big companies, huge companies, that are not directly into, you can say tech and stuff. Those want to invest in this new technology because, say, in future, in near future, when it actually becomes a, I wouldn't say reality because it's already a reality, it becomes a scalable reality, at a point where we can scale it to industrial problems. Companies don't want to be left behind. Right. They just, it's like, I mean, you don't want to start late. You don't want to start developing algorithms after we have the hardware. So they are starting to invest in developing algorithms right now for the hardware, which for the hardware that there will be after 10 years. I mean, 10 years is very large, I'm saying, but it will be within 2 to 3 years, I would say, by the scale which we are growing. So it's like
Yeah.
that. So, so that is why, so okay, now coming back to your question, so it's about the job opportunities and the monetary thing. So you see this field, because it's a niche field, so the people are limited. The smaller community means a better, what do you call, a better probability of being picked for any kind of projects. Right, and that is also the case. And because this is the niche field, again, see, the niche is the term which I'll be using a lot because quantum is a niche field. So because it's a niche field, there is no paradigm, See, okay, now if I'll ask you a very simple, I mean, if I want to hire a front-end developer right now, There's a standardized process to it, right? There's a very standardized process. I'll ask for your certifications. I'll ask what kind of projects which you have worked on, and that will be enough, right?
Hmm.
But in this quantum computing field, you're not limited to the certificate. That is why, I never use the term that, okay, even when you're in the roadmap thing, go for courses right now.
Hmm.
This might be my personal opinion, but right now, certifications in quantum computing are not that relevant. And why is that the case is because see, even if you know the basics of quantum computing at this point, does not equate that you are great, you have expertise in this, right? It's that how you grasp the concepts, how you're able to implement them into real world projects is how what defines what kind of job opportunities you can get. So this might, some people might feel like, okay, this is hard, but this is actually an opportunity. This means that you can say show your creativity. You can show your creativity. You can show how well you can perform, right? So I have taken so many interviews, like for job opportunity, for developer roles, and for hardware roles, for research roles. So we look at the CV. I'll be very honest, but we don't just selectively, you can say just you can say cut people out just because they don't have certification. We talk to them. We ask what their perspective of this project was and what they did was. So this gives you, this presence as an opportunity that you can be expressive of what you want to do, how you see this field as. So this is an opportunity for those creative people out there that feel like the education is restricting them. And about the job opportunities, where to be the job roles which you can get. You can always be a developer. Like there is a whole development aspect. You can be an application developer, you can be a software developer, and then there is the whole hardware aspect. In which help in improving the you can say the quantum hardware and stuff. And then there's the research aspect. So see, quantum being a niche field, there always be requirement of research scientists. You know, so there will be
Yeah.
people who will be doing that hard work of studying research papers and making out the feasibility and stuff. So yeah, that is again. So there are three basic, I would say, from my side. I would say opportunities. One is from research oriented, developer oriented, and I would say hardware oriented for those who comes from electronics background and stuff. And about a monetary thing, it's more than enough. And why I'm saying that is, as I said, the talent pool is limited. The people are limited. So that and every company want to get into this, right? So when there's less supply but more demand, definitely the people who are in this field will get. So to
Yeah.
answer your question, that's the case.
So
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 yeah,
that's
like informal, I would say advice from my side, but better hop in on this train sooner. Otherwise, there's a huge competition that is awaiting for you. Like because your people are hopping. Like IITs, are starting a course in quantum computing itself.
yeah.
Like IIT Madras already did, and the like education institution are hopping in on it, right?
Yeah.
So
IITs are opening.
hmm,
Many IITs are opening engineering physics branch there. Like IIT Roper is opening
exactly.
soon. Yeah.
Exactly, exactly. So yeah, that's what I'm saying. That you still have. I mean, see, I wouldn't say that when I hopped into this, it was a very, very, it was not even that, or even talk about in India. But अब they have started talking about it. So
Yeah.
this is the perfect time to hop on the train. If you're a first year student, even if you're a high school student planning to be joining an institute, this is the perfect time for that. Honestly, from my personal point of view.
Yeah.
So yeah, although it's never too late, but this is the perfect time, honestly.
Yeah. So keeping time in mind, that's it for today. And if it allows, we will make more sessions over the domains and job opportunities in quantum field. So that's all for today. I will link all the resources which Abhigyan will share, and some more resources which I will have for you to start. And so, as the T-shirt says, quantum starts here. Thank you.
Yeah, yeah, that's why I wore the t-shirt. So yeah,
Yeah.
it always starts with one step, and that is to try your
Yeah.
hand in. Read just one article. If you like it, you'll like it. Let me tell you.
Yeah.
And if you don't, you didn't waste much of your time, right? You just read an article.
Yeah.
So yeah, yeah. Thank you for the opportunity, Ashmit. And yeah, it's always good to directly address the first year students who are the
Yeah.
growing demographic right now. Yeah,
So thank you for coming here. So, thank you.
yeah. Thank you, Ashmit. Thank you.